The impeller and volute designs were computed with Gulish algorithm and the simulations were run in star CCM+. Water was simulated first to compute best efficiency point values needed for the hydraulic institute method.
To predict the viscous fluid performance, it were used correction factors for efficiency, head and flow rate. It was used by comparing the property with a liquid reference, in this case water.
For this project, water, oil, and 8 fictitious fluids were studied. Each fluid has different viscosity or density values. This is a reason for analyze the behavior of each fluid in the designated pump. For this, the current flow chart to determine viscous fluids properties was applied. The flow chart suggests 5 or less steps to calculate the fluid properties. In the current slide, it's possible to observe the 5 steps to apply the method developed by the Hydraulic Institute. In first place, parameter B is calculated. Second, flow correction is made. Third, head correction factor is applied. Fourth, efficiency correction factor is determined. And fifth, shaft is calculated.
For the MATLAB simulations, the Hydraulic Institute algorithm was performed for the 10 fluids. From this algorithm was possible to obtain the characteristics curves for the different fluids. Using these curves, it's possible to compare the behavior of the fluid obtained using different methods. The most important results are head, efficiency, and hydraulic power. The different curves for the fluids allow to see the behavior with various viscosities. When the fluid has a high viscosity, the head reach is lower. Otherwise, the efficiency for the different fluids have a similar behavior. As the figure shows, all the fluids obtain the maximum efficiency point in a flow near to 45 cubic meters per hour. However, the fluids with high viscosity obtain less efficiency. This is due to the necessary potency to pump the fluid. The figure of the hydraulic power allows to see the parabolic behavior. This potency increases with the flow to a point where the head is so low that the hydraulic power.
In this case, the Reynolds number is not significant for head value on shutoff point. As is shown in the figure, the change in head for Reynolds numbers range is approximately 0.25 meters, which is insignificant compared with the head change on best efficiency point for each fluid studied in this project. According to the current slide, for high Reynolds number values, head on best efficiency point will decrease, while for low values, head will be low. In this case, for each fluid, different factors could affect the relationship between the two values shown above. For example, viscous liquids require more energy in the best efficiency point. As energy increases, head also increases. On the other hand, Reynolds number changes the physical properties such as viscosity and density. As viscosity increases, Reynolds numbers decrease, and in parallel, as density increases, Reynolds numbers decrease its value.
For fluid number 2, we obtained that the maximum head was at the shutoff with a value of 52.93 meters. Its highest efficiency was 15.66%, and the best efficiency point was at a volumetric flow of 40 square meters per hour with a head of 33.56 meters. Now, the second fluid was fluid number 4. Its highest head was also at the shutoff and with a value of 52.74 meters. Its highest efficiency was 16.33%, and its best efficiency point was also at 40 square meters per hour with a head of 33.44 meters. The third fluid was number 7, and its highest head was also at the shutoff with a value of 55.34. Its highest efficiency was 16.4%, and the best efficiency point was also at 40 square meters per hour with a head of 33.39 meters.
The hydraulic power computed in the simulations has a similar behavior to the one computed with H-height method. Curvature means a deviation. This difference comes from the models used. CFD uses more accurate models, while HI is a numerical approximation. Higher viscosity means more power needed to reach a higher head. Then, fluids with higher viscosity have higher heads at shutoff, and fluids with low viscosities have a low head at shutoff.